Swayam Prabha. Digital India. Educated India.
Well, now we are in our 11th lecture, and today we are going to discuss the minimization problems. As the name suggests, the minimization problems basically deals with problems where the objective function is one of minimization. So some examples of minimization problems are here, like minimizing the cost of public transport facilities. See, the public transport facilities, particularly the railways, and you see those local trains that runs in suburban areas or in also in cities like Bombay or Kolkata. You can see that in those places, these local trains, they are like a lifeline to the people, and their contribution is extremely important to the lives of people. However, all these public transport facilities are always running in huge losses. So obviously the railways would like definitely to minimize the cost of such public transport facilities. All right. Here comes a very important question. That question is that, one side we have the problem of minimizing the cost, and other side, that is for the user side, there is a requirement of a certain level of facilities. So usually a balance has to be drawn, and that balance usually it comes in through some regulations that would ensure a certain level of activities to be continued for public good, right? That means there should be a threshold of activities, and that activity has to be maintained. In other examples, say for example, minimizing pollution in coal-based power plants. You see, in the coal-based power plants are one of the worst, in various industries because of their pollution. So lots of pollutions are there, and in the recent days, a lot of regulations have come in so that the coal-based power plants, they reduce their levels of pollution. An extreme step is close them down. So, but then are we in a situation, particularly in Indian context, where we can close them down? Definitely we cannot close them down because of huge requirements of power in India. And coal-based power plants play very important role in power generation. So again, there has to be a trade, there has to be a balance between minimizing pollution on other hand and generation of power on the other hand. All right, so this is also another example. Look at the mobile towers. All the companies who are running the mobile phone support facilities, they are definitely interested in putting up more mobile towers in the city areas, because in the city areas the population density is high. People talk much more on mobile phones in the city areas. On the rural areas, on the other hand, the area-wise population density is not much. So obviously it is not going to be cost effective to put up mobile towers in the rural areas. So what is going to happen? At that time, while the objective function is one of minimizing cost, but an extreme solution like no mobile towers in rural towers, which would minimize the cost to the zero level, is not going to happen. And that is because a certain level of mobile towers must also be put in the rural areas vis-a-vis putting them in the city areas. if you take the cost of gold mining, the gold mining is extremely costly. You have to get, tons of material removal, the soil removal, to get a few grams of gold. So many a time the gold mining, instead of becoming profit making, becoming a loss making venture. So again there, the gold is something which we require, and therefore a certain level of operation has to be maintained. While minimizing cost is important, a certain level of activities to be continued for public good is also very important. Now, why I said all of these in great detail is, if you look at this particular problem, which we shall take up for solving by linear programming, you see in the standard form, the minimization problems are always having greater than equal to type of constraints. And these greater than equal to type of constraints always come because that you minimize the function, but you don't minimize to such a level that the basic level of operations are hampered, right? So it is assumed this 900 and 1200 is representative of basic level of operations, and therefore the value of x1 and x2 should be such for these two resources that at least 900 of the first resource and 1200 of the second resource would be consumed. And obviously there will be the non-negativity constraints. So if you really look at it very carefully, then you find that x1 equal to 0 and x2 equal to 0 as a starting solution is not going to be realized in such problems. Why? Because if you put 0, 0, these two constraints are not satisfied. So, that means we cannot start at origin like we have done in all the maximization problems earlier. All right. So what should be done? There is a second problem also. Let us look at the augmented problem. So you see, this is a greater than equal to sign for both the constraints. So if we have to write augmented problem, if you have to really translate these inequalities to equalities, you have to, instead of adding something, you have to subtract something. And those subtractions are x3 and x4, which are called the surplus variables. So, straightway speaking, if you forget the a1, a2 for the time being, the equations could have been 20x1 plus 30x2 minus x3 equal to 900, and 40x1 plus 30x2 minus x4 equal to 1200. But that is not the case. We also require artificial variables. Why are they needed? Because if you simply leave it at the surplus variables, the surplus variables are not going to form, together an unity matrix. The matrix will be -1, 0 and 0, -1, right? That is not an unity matrix. So the canonical form is therefore not obtained. And if you know very well that unless we get the canonical form, we cannot use the simplex procedure. And therefore, to maintain the canonical form, we need additional variables. And these additional variables are the artificial variables. As such, they don't have any practical significance. They are considered simply to maintain the canonical form, and so that together they form the unity matrix. And since there is no practical significance, they should be driven out of the basis as early as possible, because initially they will be in the basis because they form the canonical form. They are in the canonical form. And therefore they should be driven out of the basis. So in a minimization problem, always they are associated with positive m profit coefficients, where m is a very, very high number. Is it all right? So that is how the objective function becomes 60x1 plus 80x2 plus 0x3 plus 0x4 plus ma1 plus ma2. All right. So that is the format that we shall going to have. Right. If you look at it carefully, then we have the original problem and we have the augmented problem. And before we start the simplex way of solving this, let us look at the graphical solution. So graphically here we have plotted the two equalities 40x1 plus 30x2 equal to 1200 is goes through the point D and point C. C is 30, 0 and D is 0, 40. That means x1 equal to 30, x2 equal to 0. Here x1 equal to 0 and x2 equal to 40. The second constraint, which is 20x1 plus 30x2 equal to 900, goes through the point A and E. Right, A is 0, 30 and E is 45, 0. Obviously, the O is not part of this. Now, what should be the solution space? Please see this is greater than equal to 900. That means if I put 0, 0 in these two constraints, the constraints are not satisfied. That means 0 is not part of solution space. What does it mean? The solution space is on the other side of 0, right? The solution space is on the other side of 0. Since there is a solution space, it is definitely a feasible solution space, right? The solution space is away from the origin. It is a feasible solution space. And the nature of the solution space, if you look at it carefully, solution space is unbounded, right? There is no bound and infinite values are also possible. But will there be infinite values? It will not be. Why? Because it's a minimization function. And the very nature of the objective function, that is one of minimization, would ensure that the problem will have a solution and it won't be having infinite solutions. All right, so that is what graphically thing is there. And here is the solution space shown by the hatched lines, and DBE, these are the basic feasible solutions are in this context of the graph, they are corner point feasible solutions, and solution space is unbounded but feasible. All right, is there an optimal solution? Answer is yes. And what would that be? It should be one of the points either D or B or E, right? It will be one of the points D, B or E. Why? Because they are the only three basic feasible solutions of the solution space. In this case, corner point feasible solutions in the context of the graph. Right. So here is the 3 points that are evaluated. Point D, x1 equal to 0 and x2 equal to 40. Point B, x1 equal to 15 and x2 equal to 20. Point E, x1 equal to 45 and x2 equal to 0. So when those values are put in the objective function, then we have 60x1 plus 80x2. So therefore, this value should be 80 into 40, 3200 at point D, and 60 into 15 and 80 into 20, that is 2500 at point B, and 45 into 60 plus 0 into 80, 2700 at point D. Now point B returns the minimum, that is 2500 only. So it's very clear that objectives function is minimized at point B. So that is our optimal solution, that is x1 star is 15, x2 star is 20, z star is 2500. Very good. So that is how the graphical solution tells us. And this graphical solution, we shall keep it with us, and we shall see later that how this graphical solution is going to help us in in our simplex solution, because the same solution should be returned by the simplex also. Right. Let us look at the simplex first table. So in this simplex first table, as I have told earlier, that A1 and A2 should be in the basis, and A1 with a value of 900 and A2 with a value of 1200. And as I said, that surplus variables x3 and x4, they are having -1, 0 and 0 minus 1 coefficient. And the canonical form is obtained. That means the unity matrix is obtained by the artificial variables A1, A2, 1, 0, 0, 1. All right. And since A1, A2 are having M as their coefficients, profit coefficients, in this case, they are called cost function. So they could be called as cost functions, cost of, coefficients. So the, how much should be the Cj minus Zj? Contribution is 60 and contribution is 80 here. Zj is 20 into m plus 40 into m, 60m. For x2 also 30 into m plus 30 into m, so that is also 60m. So for x1, the profit coefficient Cj minus Zj would be 60 minus 60m, and for x2, 80 minus 60m. So this is a minimization problem, so we shall take up one. All right. So which one is reducing the the Cj minus Zj by the maximum amount. So we see that in this case then that 60 minus 60m is lower than 80 minus 60m, although the difference is very small because m is very large. So this is not significant at all, but nevertheless x1 would now come into the basis. So which one is the bottleneck resource? We have to now find out the bottleneck resource also. The bottleneck resource, if you look at 900 by 20 is equal to 45 and 1200 by 40 is 30. So it's clear that 30 is lower, so A2 would be our leaving variable. So what happens when artificial variables leaves the basis and x1 comes into the basis? All right, so because that happens, so now A2 comes into the basis, A2 goes out of the basis and x1 comes into the basis. So you see in the next table, x1 has come into the basis, A2 has been out. And since the artificial variable is having infinite or very high coefficient, cost coefficient, so obviously it can never come back into the basis, because you see it would increase the function to a much higher value. So we need not even calculate that anymore. So A2 can be left out of calculation because it has left the basis. So now the basis is A1 and x1 and values are m and 60, the coefficient values, cost coefficient values, and the value of A1 would be 300, value of x1 will be 30, and the calculations are done in this way. The intersecting element is 40. So because intersecting element is 40, now this value 1200 by 40 becomes 30. 40 by 40 becomes 1, 30 by 40 3 by 4, 0 by 40 0, minus 1 by 40 minus 1 by 40, and 0 by 40 0. All right, then the these x1 should be x1 and a1 should now form the unity matrix. So 0 1 1 0 unity matrix is formed here, and in that order, that means a1 and then x1, and then other values are calculated by the formula. So 900 becomes 900 minus 1200 into 20 by 40. That means 1200 by 2. So 900 minus 600 equal to 300. These minus 1 minus 20 into 0 by 40. So minus 1. Like these, all the values are obtained, and Cj minus Zj is computed once again. How much it should be? It should be, you see, 80 minus 15m minus 60 into 3 by 4. How much is that? 35 minus 15m. You can also calculate by this. So 80 minus 60m minus 60 into 60m into 30 by 40. If you calculate, you will get 35 minus 15m. And this is going to be m because Zj is minus m, Cj is 0, so Cj minus Zj is m. And in this case, it is 3 by 2 minus m by 2. So again you see the lowest Cj minus Zj is returned by the x2 variable. So since x2 is having the lowest Cj minus Zj, so x2 should be now entering the basis. Which one should be leaving the basis? 300 by 15 is 20 and 30 divided by 4 by 3, that is 40. Alright, so therefore A1 now should be leaving the basis. So exactly that is what we have chosen. In the next, A1 leaves the basis and X2 enters the basis. So this is our key row. So key row intersecting element is 15. This is our key column. So every element has to be divided by the intersecting element in the key row. So A1 is now replaced by X2 in the next table. All right, and then 300 by 15 is 20, 0 by 15 is 0, and this should be 1, 15 by 15, minus 1 by 15, and 1 by 30. This 30 should be 30 minus 300 into 3 by 4 by 15, so 15. Canonical form is by x2 and x1 in that order, 1, 0, 0, 1. And remaining coefficients are also computed, and also our Cj minus Zj value. All right, so after all these computations, what we get is the Cj minus Zj is 7 by 3 and 1 by 3. So what does it mean? It means in a minimization problem, all the Cj minus Zj values are positive. See, in maximization problem, if you recall, we had a situation where all the Cj minus Zj values are negative, then we stop. The reverse will happen here because we are minimizing. So when all the Cj minus Zj values are non-negative, then we can stop. In fact, one of the special cases where one of the Cj minus Zj is 0. This means that there could be alternate solutions. Anyhow, the optimal solution is reached, and that optimal solution is x1 equal to 15, x2 equal to 20, and z equal to 2500. All right, so if you recall, the same solution that we got graphically, we have obtained here. Is it all right? So this is how we are going to solve the minimization problem, particularly with greater than equal to type of constraints. Now, just because the minimization problem we have taken has greater than equal to, and I have given logic that yes, greater than equal to is more prevalent because of certain reasons, which I explained in great detail. It doesn't mean that other type of constraints like equality constraints or less than equal to constraints are not going to be there in minimization problems. So minimization problems will have all types of constraints, and those kind of examples we shall see also at some point of time. Now there is another method in minimization problems which is known as the two-phase method. You see, it is not simply with minimization problem. Two-phase method can be applied to other kind of problems also where maximization is the objective function. Right. So what happens in a two-phase method? See, we have seen when artificial variables they are assigned with a very high cost values in minimization problem, that is plus m, calculations become a little difficult. So in order to simplify matters so that we can calculate with a little bit of more ease, the two-phase method has been devised. What the two-phase does, in the first phase, it it tries to drive out all the artificial variables. Basically, you see the presence of artificial variables in the simplex table means what? It means that the problem is basically infeasible. The infeasible solution is represented by the presence of the artificial variables. If you look at the first table once again, look here, this is our first table. A1 and A2 are in the basis. So A1 equal to 900, A2 equal to 1200. What is the value of x1? X1 is 0, x2 equal to 0. Now you see it basically means the origin. But in the very beginning, we have seen in the graphical solution that origin is excluded. The origin is not part of the solution space. We can see that also. See, look at the solution space. The origin is not part of the solution space. See, the solution space is here. The origin is an infeasible point. So, but then if the origin is infeasible, we are still starting at the origin, that is x1 equal to 0 and x2 equal to 0. How it is possible? With consideration of artificial variables, we have artificially made x1 equal to 0 and x2 equal to 0 a feasible point. So you see, the presence of artificial variables in the basis essentially means we are starting with an infeasible point. The artificial variables in that sense, their presence in the basis represent nothing but an infeasible situation, right? And we start with an infeasible point and artificially call them feasible by consideration of artificial variables. So what we do in the two-phase method, in the two-phase method, we in the first phase, we try to start with the artificial variables and try to remove the artificial variables and make the problem as a feasible problem. All right. So since removing artificial variables is the only thing, then we try to the cost or profit coefficients for artificial variable we take 1, and for the other variables we take 0. Is all right. And solve using the simplex algorithm till the artificial variable is eliminated. Now in the phase 2, restore the objective function to its original form with slack or surplus variables, but not including the artificial variables because they are removed. Rewrite the simplex table as obtained after phase 1 after the elimination of the artificial variables. Recompute the Cj minus Zj values in the restored objective function. Carry out the simplex procedure till the optimum solution is obtained. So let's repeat once again. In the phase 1, write the augmented problem with the help of slack, surplus, and the artificial variable. For the problem of minimization, rewrite the objective function with only artificial variables with profit coefficient or cost as may be value as 1. That means rest of them are all considered as zeros. So solve using the simplex algorithm till the artificial variables are eliminated. And in phase 2, now restore the objective function to its original form with slack surplus variables, but not including the artificial variables because they are now driven out. And now rewrite the simplex table as obtained after phase 1 after the elimination of the artificial variables. Recompute Cj minus Zj values with the restored objective function, right? So this is the procedure, and then carry out simplex procedure till the optimum solution is obtained. So the removal of artificial variables and solving the rest part of the problem, they are now separated out in two different phases, right? And also M is not required. +1 is sufficient for a minimization problem as the profit or cost coefficient for the artificial variable. Right. So here is the phase 1. See, look what has happened. Objective function is changed to simply a1 plus a2. Rest of it is not considered. Right. So if you look at the coefficients, the Cj coefficients are 0, 0, 0, 0, 1 and 1. And the Ci is 1 and 1. All right. So therefore, it's very clear that for x1 and x2, Cj minus Zj will be minus 60 and minus 60. For x3 and x4, it will be 1 and 1. Right. So there is a tie, and Cj minus Zj for both x1 and x2 are equal to minus 60. So any one of them can actually be selected. We can select x1 as earlier, and then we see that for a1 it is not bottleneck, but for A2 it is bottleneck because 900 by 20 is 45 and 1200 by 40 is 30. So x1 is entering variable, A2 is leaving variable. Let us see that x1 is leaving and A2 is x1 is entering and A2 is leaving. Right, so that computation is done once again, and this is the key row. So 1240 is the intersecting element. So 1200 by 40 is 30. This is 1. This is 3 by 4 for 30 by 40 for x2. 0 by 40 0, minus 1 by 40 minus 1 by 40, 0 by 40 0, and A2 is dropped because once the artificial variable goes out of the basis, it can never come back into the basis. Isn't it? That is the basic philosophy we had already discussed. All right, then the remaining calculations could be carried out. That is, these 900 would be 900 minus 1200 into 20, corresponding key row element into corresponding key column element divided by the intersecting element. So that would be 300. Similarly, all the other values are computed, and you see x1 is having Cj coefficient, Ci coefficient 0, Cj also 0, and therefore for x2 Cj minus Zj will be now minus 15. Why? 0 minus 15 into 1, so minus 15. Here 0 minus half into 1, so minus half. Here 0 minus 1 into minus 1, so plus 1. All right, so which variable should be entering now? It should be x2. Why x2? Because it has the most negative Cj minus Zj value in a minimization problem. And then which one should be bottleneck? A1 should be bottleneck because x2 enters, and here 300 by 15 is 20, 30 by 3 by 4 is 40. All right, so then x2 enters the basis. So this is our second table and this is our third table. So this is our key row. X2 has come into the basis. A1 is driven out, so it is dropped. So the values are 300 by 15. 15 is the intersecting element. So 300 by 15 is 20. 0 by 15 0. 15 by 15 1. Minus 1 by 15 minus 1 by 15. Half by 15 1 by 30. Right? This value which was 30, it should be 30 minus 300 into 3 by 4 by 15. That means 30 minus 20 into 3 by 4. So 30 minus 15. So it should be 15. And canonical form between x2 and x1. So 1 0 0 1 in the reverse order. And here the remaining coefficients are all computed. And now we find Cj minus Zj value is 0. So artificial variables are all eliminated and phase 1 is completed. So this is how we complete the phase 1. And once the artificial variables are driven out, we get this solution. But this is only an intermediate solution. What we have to do now, we have to replace the Cj and Ci values with their appropriate values. So what are the appropriate values? 60 and 80. And here 80 and 60 because x2 is here. So now when you put them and then compute Cj minus Zj, then we see that they are all positive. So that means the first table itself is optimal solution. All right, so objective function is restored and Cj minus Zj values are recomputed after the elimination of the artificial variable, and therefore the optimum solution is obtained, that is x1 star equal to 15, x2 star equal to 20, and z star equal to 2500. Once again, let us see. So this was our table. In this table, the Cj values of x1 and x2 were all zeros. All right. So what we do now, since the artificial variables are all removed, we restore the objective function. So by restoring the objective function means the original Cj coefficients are brought back. So what is the original Cj coefficients? Because the objective function was 60x1 plus 80x2. So original Cj coefficient for x1 is 60 and for x2 is 80. So those 60 and 80 are put back, and after putting back, the Cj minus Zj's are computed again. Then for x1 and x2, because they are in the basis, they are zeros, and x3 and x4, because they are non-basic, has to be calculated, and that calculation comes to be 7 by 3 and 1 by 3. So in a minimization problem, both the Cj minus Zj values are positive. That means optimum solution is reached. And therefore, we report the optimum solution, which is x1 equal to 15, x2 equal to 20, and z star equal to 2500. All right, so I hope you understood that how these minimization problems are solved. First of all, we need artificial variables, unlike maximization problems with only less than equal to constants. And most of the time, minimization problems are going to have greater than equal to type of constraints. And these greater than equal to not only require a surplus variable, but also require artificial variables. And these artificial variables are to be driven out. And there are in the two-phase method, what we do, we first drive out the artificial variable by suitably modifying the objective function so that the computations are simple. And after the artificial variables are driven out, then we again bring back the original objective function and then compute from there. Right. Now that you have understood, let us take another problem. All right, so this problem is interesting because it has got all different types of constraints. All right, so minimize z equal to minus 3x1 plus x2 plus x3 subject to x1 minus 2x2 plus x3 less than equal to 11, minus 4x1 plus x2 minus 2x3 greater than equal to 3. So there is a less than equal to constraints. There is also a greater than equal to constraint. And 2x1 minus x3 equal to minus 1. And this third one is another one where we have an equal to type of constraint. So all three types of constraints are there: less than equal to, greater than equal to, and equal to. And third one, since the right hand side is minus 1, we replace it by multiplying minus 1 to both sides and say minus 2x1 plus x3 equal to 1. And let us say that non-negativity constraints are also there: x1 greater than equal to 0, x2 greater than equal to 0, and x3 greater than equal to 0. Now, before we begin, it's a minimization problem. So tell me, how many artificial variables will be required? How many artificial, which are the constraints which require artificial variable? If you think very carefully, then you will find that less than equal to constraints do not require any artificial variable. Why? Because you can simply add a slack variable that is sufficient, and it will have a coefficient of +1. So there won't be any difficulty in bringing it into canonical form. But greater than equal to, as we have just now seen in the problem that we have discussed, there we need a surplus variable, and we also need, which is having a -1 coefficient, and also need an artificial variable. Similarly, that equality constant, that also would need a an artificial variable. So it is very clear, it will need a slack variable in the first constraint. It will need a surplus variable and an artificial variable in the second constraint, and it will require an artificial variable in the third constraint. Is it all right? So all the three types are required. So that is what is going to happen in this particular problem. We need one slack, one surplus, and two artificial variables, right? So this is what has been done, and the augmented problem is written. So you look, the first constraint requires an slack variable, which is x4. So x1 minus 2x2 plus x3 plus x4 equal to 11. The second constant, which is greater than equal to, require a surplus variable x5 and an artificial variable a1. All right. So minus 4x3 plus x2 plus 2x3 minus x5 plus a1 equal to 3. The third one, which is an equality constant, problem is that with equality constant, unless we take a variable, because as such, it is inequality, so it appears, then why should I add one variable? See, the canonical form, that means at least one variable should be such that is there only in that particular constant. It is not there in any of the other constants. Look, x1 is there in all. X3 is also there in all the constants. So we don't have a variable which is occurring with a +1 coefficient only in these constraints, because that is what is required in canonical form so that the unity matrix can be constructed. All right, so that is why we need a variable, and that variable is an artificial variable. So you see here x4, a1 and a2 together, they will form the canonical form and they will form the unity matrix. All right, so here is the objective function: minimize z equal to minus 3x1 plus x2 plus x3 plus 0x4 plus 0x5 plus ma1 plus ma2. All right. So this is how the augmented problem is obtained. Now, if we write the simplex first table, what are the variables which are going to be in the basis, right? If you think carefully, you will see x4, a1 and a2 will form the basis. What should be the values? 11, 3 and 1. All right. So here is the table. x4, a1 and a2 have formed the basis. The values are 11, 3 and 1. The coefficients are here 1, minus 4, minus 2 for x1, minus 2 and 1 and 0 for x2, and 1, 2 and 1 for x3, right? Because this third constant, x3 has a minus coefficient, so that is how it is written. All right. Now, after writing these coefficients, then we see that a1 and a2 and x4 together they form the unity matrix. All right, and the cj minus zj values are computed once again, and then we find that it is the yeah, so that was a mistake. This is not minus x3, that should be plus x3, right? So minus 2x1 plus x3. So that is why that x3 coefficient is 1. So this minus should be plus. That was a mistake. That is why it was looking little bad. But then there is that problem is cleared. His same thing about here also. This is not minus, this is plus. So these both are plus. So plus 2x3 plus x3. Anyhow, so there is no problem now. And therefore, after we compute the cj minus zj, you see minus 3 plus 6m, because both are minus. For x2 it is 1 minus m, and for x3 it is 1 minus 3m. All right. So therefore the x3 should be the variable that should be coming into the basis. Because why x3? Because that is the lowest possible cj minus zj. So which one is the bottleneck resource? See, 11 by 1, 3 by 2 and 1 by 1. So 1 by 1, that is equal to 1, is the least. So a2 should be leaving variable. So exactly that is what we have done here. A2 is leaving and x3 should be our entering variable. So now A2 has entered, sorry, x3 has entered, and here since 1 is our intersecting element, so there is no change here, and canonical form is maintained by the variables x4, a1 and a2. Look, x4 is 1 0 0, a1 is 0 1 0, and x3 is 0 0 1. All right, so these are easily calculated, and they start calculated by formula. So 11 minus 1 into 1 by 1. So here original element minus corresponding key row into corresponding key column element minus the intersecting element. So this 11 would be 11 minus 1 into 1 by 1, so 10. And this 3 should be 3 minus 1 into 2 by 1, so that should be 1. Is it all right? So like these, we compute the values and rest of the coefficients are also computed. All right, and thereafter, when again we compute Cj minus Zj, that time we find that it is minus 3 plus 2 equal to minus 1. And here it should be 1 minus m, and here it should be m. All right, so 1 minus m is the least. So it is very clear that x2 now should be coming into the basis. All right. So if x2 comes into the basis, which variable should be leaving the basis? Look, it should be a1 because 10 by minus 2 is not bottleneck. 1 by 0 not bottleneck. 1 by 1 that is the bottleneck. Because you see you don't need resource because it is releasing resource, and here resource is not required, and here only one resource is required for a1, but then it is only one is available, so a1 should be leaving the basis and x2 should be entering the basis. So that is what has happened, that is a1 leaves the basis and x2 enters the basis, right? So when we recompute, at that time we find that x4, x2 and x3 they form the basis, and these a1 is replaced by x2 and a1 is dropped also. So this should be now 1 0 1 0 0 minus 1. This is dropped. So that should be our key row. The key column, the unity matrix is formed by x4, x2, x3 in that order. x4 1 0 0, x2 0 1 0 and x3 0 0 1. All right, and remaining coefficients are all computed. So here 10 minus 1 into minus 2 by 1, so 10 plus 2 12. These 1 should be 1 minus 1 into 0 by 1, so it remains 1. So like these values are obtained and all the other coefficients are computed, and once again the Cj minus Zj is computed. Now you see again x1 comes into the basis. So which one is the bottleneck resource? x4, because it is 12 by 3 4, 1 by 0 not required, 1 by minus 2 not required, because 0 or minus if it is the coefficient values in the coefficient matrix, they are not going to contribute towards the bottleneck resource. So therefore x1 now comes in again into the basis and x4 would be the leaving variable. All right, so that computation is done, and after that computation we see that this is the key row element, intersecting element is 3. So every element is divided by 3, so it is 4 1 0 0 1 by 3 minus 2 by 3. And x1, x2, x3 forms the basis, so they should have a canonical form. So you see 1 0 0 0 1 0 0 0 1. That is how this matrix is formed. And other values are calculated. This 1 minus 12 into 0 by 3 1. This 1 minus 12 into minus 2 by 3, so 9, right? And rest of the coefficients are computed, and when Cj minus Zj value is again computed for x4 and x5 which are not in the basis, we see they are 1 by 3 and 1 by 3. All right, what does it mean? That optimum solution is reached. So what is the optimum solution? 4, 1 and 3. So Z star is minus 3x1 plus x2 plus x3 equal to minus 2. So that will be the optimum solution. All right, so we have seen that how these kind of problems are solved, and as a special exercise, let us also see how this same problem can be solved by the two-phase method. So this is the two-phase method explained once again. We know that we have to rewrite the objective function with only artificial variables with all profit coefficients equal to 1 and solve the simplex algorithm till the artificial variables are eliminated. And what happens in phase 2? Restore the objective function, rewrite the simplex table as obtained after phase 1 after the elimination of the artificial variables. Then recompute the Cj minus Zj values with the restored objective function. Carry out the simplex procedure till the optimum solution is obtained. All right. So this is how the process is done. I have already explained with one problem. So let us try once again. So this is our first table. In this table, look at that Cj, everything is replaced as 0, excepting A1 and A2, which are 1 and 1. All right. And therefore, the Cj minus Zj values would come at 6, minus 1, minus 3, and 1. Right. The least is minus 3. So therefore, x3 should be now coming into the basis. The bottleneck resource in this case is A2. So A2 should be leaving the basis. So precisely that's what we have done, that x3 comes into the basis and A2 leaves the basis. So if A2 leaves the basis, x3 comes into the basis, and with the values of 1, minus 2, 0, 1, 0, 0, 1, all other values are computed, and this 10, 1, 1 is obtained as values, and the Cj minus Zj values would be now for x1 is 0, for x2 minus 1, for x5 is 1, and x4, a1, x3 in that order, x4 1, 0, 0, a1 0, 1, 0, and x3 0, 0, 1. They form the unity matrix to bring the canonical form. Right? So again we see that x2 is the entering variable because we have a minus 1 there. Which one should be leaving variable? It should be a1. All right. So this is what has been done. X2 is entering and A1 is leaving. So when we do that, then we find this new matrix, that is X4, X2 and X3. All right. And the values are all computed because 1 by 1 is 1. 10 minus 1 into minus 2 by 1, so 12. 1 minus 1 into 0 by 1, so 1. So values are obtained. Rest of the coefficients are obtained. X4, X2, X3, you see they form canonical form. So X4 1, 0, 0, X2 0, 1, 0, X3 0, 0, 1, and Cj minus Zj value will now compute as 0. So now artificial variables are eliminated and the phase 1 is complete. Right? So after phase 1 is complete, now restore the original objective function values, and then we find that Cj minus Zj is minus 1. All right, so that means it is not optimal. We need to do more steps. Which variable should enter? X1 should enter. Which variable should leave? X4 should leave, because 12 by 3 is 4 and these two are not requiring resources. Right, so X1 enters, X4 leaves. So we do that, and when you do that, then you see this is our key row. So intersecting element is 3. Everything is divided by 3. So we get 4, 1, 0, 0, 1 by 3 minus 2 by 3, and 1 minus 12 into 0 by 3, 1. 1 minus 12 into minus 2 by 3, 9. And rest of the values are computed again. So what we get as our Cj minus Zj, 1 by 3 and 1 by 3. What does it mean? That the optimum solution is reached, and the same optimum solution is returned here also. That is x1 star equal to 4, x2 star equal to 1, x3 star equal to 9, and z star equal to minus 2. All right. So what we have done, we have solved the basic minimization problem. One problem we have taken where we had only greater than equal to type of constant, and we had to take surplus variable as an artificial variable for both the constant. And apart from that, a second problem also I have shown you where there are all 3 type of constraints, that is less than equal to, greater than equal to, and also equal to. All right. So this is how we solve the minimization problems. Thank you very much for patiently hearing this lecture.